Okay, good afternoon and welcome to MAE 113, Calculus for the Liberal Arts. My name is Richard Kaur and this is tutorial 4. It's not so much about new material that we're going to do. We're going to do some more exercises. More exercises in integration. Excellent, and thank you for giving me a thumbs up for the audio. Because I had posted a new assignment. You can check that out on the Moodle website. Thank you, Mr. MAE. I have posted a new assignment. Again, we don't have a quiz. You should try to do some of the exercises off of it. But surprisingly, we had covered quite a bit in the textbook as well. But as well as a little bit, we did the substitution rule, which is not in that Calculus 1 book. I think it's in the second volume. So instead of having you download a second textbook and with answers, and I've written out some questions for the substitution rule. So we can do some more examples. Okay, so in this one, we're going to evaluate the integral from 0 to 2 of x e to the 2x squared dx. And we're going to use the substitution rule. And just looking at the chat, what should I use for my substitution? I'm just looking at the chat. Does anyone have an idea of what u should be for our substitution? Yeah, the 2x squared. Yep. Let's try that. And it's a good guess, I'm saying guess, but it's a good substitution. And if we see that we have the 2x squared, taking the du, we're going to differentiate this. So I have 2x squared, so that becomes 2 times 2 is 4, x, and that reduces down by a degree, so it's just 4x dx. So I can rewrite that, or I could rearrange this a little bit. So I have e 2x squared dot x dx. Now, over here, this isn't quite matching to what I have over here. So again, I can bring that forward to the other side so that I have a quarter du, and I have x dx. So now I can rewrite that over on this side here. That's equal to 1/4 du. And I can write this as e to the u. I can bring out that 1/4 in front because it's a common multiple. And I have my integral of eu du. And this is a nice easy integral because we know that the integral of e to the u is just e to the u plus a constant because I've taken my integration now. And now I can substitute in, maybe I'll write, oh, I can fairly do that. So I can substitute that in now back into the e to the 2x squared plus a constant. Now again, we have to be careful because this is what we call we call this a definite integral, and it has the limits. We have limits of integration from 0 to 2. So we're not quite done yet. What we've done is we've solved the indefinite, so we have to solve for the definite part. So that's equal to 1/4 e to the 2x squared, and we're going to evaluate that from 0 to 2. So we substitute that in. So it's going to be this function evaluated at 2 minus this function evaluated at 0. So I have 1/4 e to the 2 times 2 squared minus, and then I'm going to evaluate this at 0. So that's 1/4 e to the 2 times 0 squared. Two squared is 4. 4 times 2 is 8 minus. Over here I have 0 squared, so that's 0 times 2 is still 0. So I get 1/4 e to the 0. E to the 0 is 1. So I'm left with e to the 8th minus 1/4. And I could factor that out. So I have e to the 8 minus 1. And so there's our answer for what we had originally, which was the integral from 0 to 2 of x e to the 2x squared. Okay. So that's the end of that example. So what that is basically in this equation, or this example, it's showing how to evaluate an indefinite or a definite integral. Okay. Now in this example, I'm going to do it two different ways. This one is, we're going to use finding the area. So we're going to find the area. Between y equals x squared plus 1 and y equals x. And we're going to do this from x equals 1 to x equals 3. So the first tip I would say is, draw a picture, draw a figure. if it's not asked in the question on the exam, or like, I'm not sure what, because we were also, there's a little bit of coordination between the two sections, but, or three. So in terms of that, if it doesn't say draw a figure, I would still sketch one. So sketch a figure, and after all those high school lessons, we know that this x squared plus 1 is a parabola. So it's a parabola going up, and it's shifted up by 1. So we know that here, that should be at 0, 1. And the other thing we can draw is the y equals x. And what they want us is the area between, we have these two curves, between, sorry. So between x equals 1 and, say 1 and 3 here. And what they want is, so that area that's bounded between that. So right in here. Now we can't use any, I can't think of a way to do this with elementary kind of like geometry that we've learned, or like with a triangle. So what we can do is we'll kind of do this in, we're going to do this in two solutions. So here's solution 1. And I'm going to call this the indirect method. So for the indirect method, I'm going to draw out 3 of these. Okay, so for the indirect method, what we're going to do is we're going to calculate the area under x squared plus 1 here. So we're going to do it from 1 to 3. I'm going to use, say, blue. So we're going to calculate all that area in here. And then I'm going to subtract the area here and hopefully what is left, I drew it a little high here, but and that hopefully what I have left is kind of this area that's remaining. So the idea is that I have this total amount of area. I'm going to subtract what's underneath this area here, so that I should just get that the area that I want, which is this region R. So I'll call that R. So is everyone okay with that so far? What am I about to do? So you can think of that as the total area. This is the area I'm going to take away, and I should have the area that I want remaining. And that's why we were calling it the indirect method. So for this one, so here's A1 and here's A2. That should be my R. Okay, perfect. So in this, I have A1. We're going to integrate from 1 to 3, because that's what we're asked, 1 to 3 of this curve here, so x squared plus 1 dx. And we integrate that using our power rule, so x squared becomes 1/3 x cubed plus x, and we're going to evaluate that from 1 to 3. And this is a warning again. We're going to evaluate this at 3 and at 1. So I'll substitute my value in for 3. But be very careful, because this is, I need the negative here. And it needs to distribute over that function at 1. So just you need to distribute that negative. So 1/3 at 1 cubed plus 1. So I get 27 over 3 plus 3 minus 1/3 minus 1. I get 9 plus 3 minus 1/3 minus 1. That's 11 minus 1/3. Rewriting it over 3's. I get 32 over 3. Over on this side, this one's a little nicer. I have my area 2, and we're going to integrate from 1 to 3 of x squared dx. So that becomes 1/3 x cubed from 1 to 3. And I get 1/3 3 cubed minus 1/3 times 1 cubed. So I get 27 over 3. Oh, no. Oh. No, sorry. I made a... because it's... I don't know why I wrote a square there. Because it should be a straight line. Yes, thank you. Isn't that y equals x? Yep, it is. So instead, let's pull out this. It should be a half x squared. And then, substituting that in, I get 3 squared minus a half times 1 squared. So 3 squared is 9 over 2 minus a half. So I should get 8 halves, and 8 over 2 is 4. So that means, therefore, the region, the area of the required region is r is equal to 32 thirds minus a fourth and that equals 20 over 3. How's that? So that was the first solution. So you can do it that way. That's fine. So that's the indirect method. We can also do the second solution. So this one is called the, I call it the direct method. And again, I would start out with drawing my picture here. So I'm going to just sketch it again, because I need to do a little bit of a labeling. So there's my y equals x squared plus 1. Oops. There we go. So that's the region that we want. So instead, what we can actually do is come up with a function that describes that. And the way that you can do that is at every point along this curve here, it's going to be this top, the top function, and this one is the bottom function. Here's y equals x. This is the bottom function. And just along in here, at every point along here, we're going to just, for example, let's just look at this one line right here. I will have it here, and I also have that point down there. So the length of that line is the top minus the bottom. So that's all it is for coming up with that direct formula. So if we're going to integrate that, we know we're going to go from 1 to 3. I'm going to write my brackets here, dx. And so in this case, it's always going to be the top function, x squared plus 1, and we're going to subtract. So what we do for the top here, we end up getting this entire length here, all the way down to this y equals 0 here. But we'll also then subtract the y equals x part here. So that bottom function. So we actually get that length that we wanted. So here is the bottom function. And you can simplify that so that instead what I have is x squared minus x plus 1 dx. And then integrating that, I get 1/3 x cubed minus a half x squared plus x evaluated from 1 to 3. And so I just substitute those values in. So this function evaluated at 3. Minus, I need to subtract this function evaluated at 1. And again, I put the brackets around because this negative has to distribute. So it has to apply to each of these. And if you don't, well, you know that you are going to have the incorrect signs, and then you'll have an incorrect sum. Okay, so 3 cubed is 27 over 3. I have 9 over 2 plus 3 minus 1/3 plus, again, so I have that minus and a minus becomes positive, so there's the plus a half minus 1. Let's see. I have a minus 9 halves and a plus 1 half, so I'm going to write that as minus 8 halves, which we know is minus 4. I have 3 and minus 1, so that gives me plus 2. Over here then, I have 27/3 minus 1/3 gives me 26 over 1/3. Four minus 2 is minus 2. 26/3. So I'm left with 20 over 3. So it's 20/3, and what's good about that is I have from the first solution, using the indirect method, that the area is 20/3, and by this second method, or the direct method, I also still get 20/3. So I'm pretty confident that the answer is correct. So those are two different methods. You can pick which one you prefer. But I will say, with the direct method, be very careful about making sure which function is on the top and which function is on the bottom. Because if you mix them up, if you did say x minus x squared plus 1, you get an incorrect area. So, same thing. Again, I would say drawing a picture also helps. Oops, there we go. So in this case, we're going to find the area of a region. So finding the area. Of the region bounded by y equals x squared and y equals 2x minus x squared. So again, because you could just start to do the indirect or the direct method, and you could go, okay, I'm going to subtract, you know, the x squared minus 2x minus x squared. And immediately you would have an oops. Because, let's draw that out. So I have my quadratic here. And I have a quadratic, and it's a little bit bigger. It's kind of doing something like this. And so I think, you know, something like that. Don't think I drew it very well, but there's our region, or the region R. And you notice here, this is our function 2x minus x squared. And over here is my x squared. And this is the top function, and this is the bottom function. And we've put it in the wrong order here, because over here what you've done is done the bottom, and over here is the top. So the integral that we need, that we want, so this one's wrong. So the one that we want integrating from, so we have the top function, which is 2x minus x squared minus x squared, and here is the dx. Okay, we're asked to find the area, but what else am I missing? What else am I missing from this? From this in particular right here. Intercepts. Yes. What we need here is we need those limits here. We need the limits of integration. And to do that, what we need is these points here. So points of intersection. Between the true graphs and not the y-intercept. Yes. Yep. So to do that, we find out where they're both equal to each other. So we have x squared minus 2x minus x squared. And I can isolate to one side, so I'll bring everything over to here. So I have x squared and minus x squared, so that comes over here, and that becomes 2x squared minus 2x, which we can solve by factoring. So just factoring out the 2x, I'm left with x minus 1, which means that x equals 0 and x equals 1. So what I need to do is from 0 to 1 of 2x minus x squared minus x squared dx. I can simplify that. 2x minus 2x squared dx. And then we can integrate. So what should I have for the integration then? So I just need to know what the integral is for that. I'm just waiting for if anyone in the chat will put it in the. What should I expect? Yes, that's correct. The x squared minus 2/3 x to 3. Yes. So Mr. Walker, Mr. Frampton, I see that that's, yep, what Mr. Maple says what they say. Yep. So that's correct. Then we substitute in our value, so we're going to evaluate that at 1 minus this at evaluated at 0. So I have 1 squared minus 2/3 to the 1 cubed minus 0 squared minus 2/3 0 cubed. So I can see that this is 0 and this is 0. So again, that just, we don't bother with that. I'm left with 1 minus 2/3, or that's equal to 1/3. So we did that one. So again, I would say just be very careful about what function is the top function and which function is the bottom function, and making sure that you have the correct order when you pick them. Just because that they're presented this way, like with x squared and 2x minus x squared, that's not the order that you have to necessarily do it in. And then when we don't have the limits of integration, then that requires us to find them, and that will require us to find the points of intersection. Was the diagram a little bit? Yes, it was. That's what I said when I was writing it. Yep. I keep dropping papers, but yeah, this should have been, this point here should have been at 0. Yeah, that should have been at 0, 0. And over here, this should have been 1, 1. So yeah, it should have been translated. Yeah. It is good enough for what I needed it. No, it's not a curve sketching question. If I had calculated those points and I was going to grade the sketch, yeah, there would have been points taken off for that. But without knowing or doing anything previously, I just needed to know what was top and the bottom function. More examples. So in this one, we're going to say that we're going to look at a rate. So there's the rate at which radios, so it could be like walkie-talkies or I don't know, stereo system, so just radios. It can be assembled by an average worker. So it's an average worker at a company. T hours after starting work. And they say we're going to start at 8 a.m. And it's given by a function, so we have a function. We have f of t is equal to minus 3t squared plus 2t plus 15. And we're going to say that the domain is from 0 to 4. We're asked, determine how many radios can be assembled by an average worker in the first hour. Okay. So the thing for this is to remember is that this is a rate. So very similar to like when we were doing with velocity, to get back to kind of the total number of it or the displacement, we need to integrate. So again, we have a rate And what we're going to do is we're going to integrate over that rate to get the total number of radios. So again, I'll do a quick sketch. I don't know what this may look like, but what I can tell you is that from that minus 3t squared, I kind of expect it to kind of look like something like that. Concave down. And what we're asked is to integrate from 0 to 1. So this would be the rate of radios that somebody is producing. And when you look at the area, so that would be how many radios that they would have made. So again, just quick sketch. I have no idea where the vertex is. I don't know where the X or Y or where it's intersecting, but I just know that it's concave down. So if we integrate that, it'll be from 0 to 1. And we take the rate, we'll integrate that. dt. And if we integrate this, I get t, this goes up a degree, and in the denominator it's 3 as well. So I get minus 3 over 3 t cubed plus the t goes up to t squared. I have it divided by 2 plus 15t from 0 to 1. I'm going to simplify that. It's a little nicer. So I got minus t cubed plus 6t squared plus 15t. And then I substitute in my values. So I get minus 1 cubed plus 6 times 1 squared plus 15 times 1 minus everything inside here. So minus 0 cubed plus 6 0 squared plus 15 times 0. So again, every term is multiplied by a 0. So again, that disappears. So I'm left with minus 1 plus 6 plus 15. And that equals 20 radios. So the average worker produces 20 radios in the first hour of their shift, of the morning shift. So again, it's just reading this question and seeing that this is a rate. Now, I mean, if that was confusing, if you had some function, like let's use a very basic function. And let's say that if I was a worker, let's say I'm not a very good worker, let's say that my rate makes radios, and my rate is I make 1/3 T. Radios per hour. Okay, so that would be my rate. So again, it does help to have the units here. So this would be my rate, f of t. Oh, and let's not use t. Let's just do 1/3. So we'll do 1/3 and do 1/3 radios per hour. So there's my rate. So when I do this, I get my t, and this is the, over here would be like my rate. So there is my f of t equals 1/3. So that's my rate. And if you ask me then, how many radios did Richard make in 1 hour? Well, at that point, what you would do is you would look at the area. So here, 1, 2, 3. It would be that. So it's my rate. So I'm making 1/3 over 1 hour. So 1/3 times 1 should give me my total number of, so that would be my area. So the area is equal to 1/3 radios per hour times 1 hour. And this is why I like to use units sometimes. What you can see is that the hours cancel, and I'm left with 1/3 radio. Now to express that with an integral, if we integrate that rate, then what I get is 1/3 t from 0 to 1. And I get 1/3 times 1 minus 1/3 times 0. So that equals what we wanted. So how many radios does it take to make, how many hours does it take Richard to make one radio? Well, that's easy. It's 1/3, 2/3, 3/3. So it'll take me 3 hours. Yeah, exactly. Exactly. It takes me 3 hours. But if we wrote this with an integral, sometimes we might want to write something like this. Well, we know from 0 to, we don't know what it is. So let's say a, we'll have 1/3 t d. I keep writing that t. And we know we want that equal to 1. Then what I have then is 1/3 A minus 1/3 times 0. So that cancels out. So I'm left with 1/3 A, and then A, bringing that 3 over to the other side, A equals 3. So again, that idea of if we're given a rate, so if they're told how much, say, water is flowing out of a hose, you're told, 27 liters per hour, and then you asked how much water flowed out of it. You just need to know how much time that you're given, and you would know the volume of water that you needed to. So again, to get from a rate to kind of the total that's produced, that you have to integrate it. Okay. So again, just as a little review, if I had this function, I'll say this is v of t, and v of t is the velocity of the car, just of a car. And we'll say that t is in hours, and that the velocity of the car is in kilometers per hour. What does this mean then? What does this represent? I mean, mathematically, this is over here. I can do the integral from 1 to 3 of v of t dt. Displacement of distance, yes. The highway driving, close. What this represents is, you can think of it as distance traveled or the displacement of the car. But we also have the added information that it's between from 1 and 3. So between t equals 1 hour. And so what this says is if you had some sort of recording device on your car, and what this area between 1 and 3 is the amount of distance traveled between hour 1 and hour 3. Yep. But just a little bit more than just what everyone's been saying, just the distance travels, but it's also specified between those 2 time points. So there's a little bit more information now. Good. So what are some other things that we can look at is that so more properties of the definite integral. I mean, I don't really consider this more more theory, because I think if we think about it, you can think of it more, you can think of it as an application or whatever. But let's say here I have some curve. Here's f of x. And I have here an a. What do you think the integral from a to a of f of x dx is equal to? Yes, it is 0. Yes, it's 0. So there's like a property 1. It's 0. And if you want to think about that, the reason for that is if I have my big F, so again, that's where it's kind of like my integral. So my big F of a minus f of a, that will always be 0. So you can think of that as we're going from a to a, but that means that it's just a line, and a line doesn't have any area. So the area of a line is 0, and that's how we get that property. So you can have a really heinous looking integral that you might not be able to solve. But if I have the limits are the same, that is equal to 0. Okay, what else can we do? The second one that I can think of is just realized I was behind on the stream when I okay. No worries. The follies of technology. So the other one I can think of, here's another one. If I change the order of my limits. Then if I do that, it changes the sign. The reason for that is, if I think of something like this, and I'm going to go from, say, A to B, well, for this one right here, the way that we usually think about that is we usually integrate up to B, and we subtract the area up to A, and that's what we get. We get that area in between. Oops. But now instead, if I've changed it, I'm subtracting that area minus this. I end up getting this in the middle here, but it's the negative of it. So again, it's just, instead of going from A to B, in this one, it's going from A to B. So that gives me the positive. Or if I do it this way, now I'm going to get negative area. So, okay, we'll use a numerical example. So, we know how to do that. Taking the antiderivative over becomes 1/3 cubed from 0 to 1. Okay. And if we change the order now, we go from 1 to 0, x squared dx. From 1 to 0, and now I have 1/3 times 0 cubed minus 1/3 times 1 cubed. This is 0, and I'm left with minus 1/3. So, changing the order of the limits changes the sign of the answer. So is everyone okay with that? If I change the order of the limits, I get a negative sign now. Is everyone okay with that? I don't know if everyone is keeping up in the stream. Maybe it's a couple seconds delayed. Okay, good. Let's see, there's another third one. I think before I write it out, I'll show you. Something like that. And the idea behind this is that if I have, here's A, here's C, and B, the idea is that if I have the integral from, and I'm going to call this f of x, from A to C here, that's this area right here. And from here to here, from C to B of f of x dx, that's all this area here. That area, if I wanted to add those two areas up, that's equal to from A to B of f of x dx. That's it. So if you split them up and A is less than C is less than B, so the C is in the middle between A and B, kind of like it's splitting it up, then if you sum those two up, we would expect it to be the sum. So that's it. So if I have this original integral, A to B, I can break that up from A to C plus from C to B, where A is less than C is less than B. So for example, I could have something like this, which is from 0 to 1, f of x dx is equal to 0.3. The integral from 1 to 2 is equal to 0.4. So then what is the integral from 0 to 2 of f of x dx? Will I be discussing exam specifics at the next class? Yes. I will go over the format, what to expect, and then also it's supposed to be kind of like a review. It's going to be of all the things that the topics that we've covered. but I can tell you that it's going to be a 3-hour invigilated exam. It will, I'm not sure how many questions we're going to have yet, but there'll be questions that you answer on paper, long form, long style. We don't have any multiple choice questions on this. So that's kind of giving you a little bit of a preview for Thursday's class. It'll be cool. It'll have a PowerPoint presentation and everything. You won't have to look at me writing. Okay, so in this case, I'm going to use from 1 to 0, 1 to 3, g of x dx equals 2 from 0 to 3. So this one is a little different because I can't just go from 0 to 1, 1 to 2. I have from 1 to 0. So in order to handle this, from 0 to 1, if I want to flip or change the order of my limits, well, using that second property that we just did right here, I know that this will be negative 0.8. So now I can do it from 0 to 1, 1 to 3. So from 0 to 3, that's equal to 2 minus 0.8, and that equals 1.2. Okay. Let's jump over to Moodle. So I've already posted assignment 11, so I'm just going to switch over to screen. So here is our assignment 11. Again, there is no quiz. These are questions that we'll still have to do, but we have like the definition of the integral, fundamental theorem of calculus, definite integrals, and then about 3 questions on the applications of the integral. So that's like, if I remember correctly, it's, given the velocity, find the displacement or the total distance traveled. But there's lots of, you'll have like, given the substitution, evaluating the indefinite integral, evaluating the definite integral, finding the area between the curves. And again, I would say include a sketch of your region. That's a helpful hint. Some of them will give you the limits of integration. So A through C will give you the limits of integration, while D through F doesn't. You'll have to find the points where they intersect. Maybe I will look at that question. So just switch back to the paper. So this is from, let's say, number 9. From the assignment 11, or sorry, this is 12. Here's number 5. So if I have f of x dx is equal to 1/9 x to the 9th plus c, then what is f of x? So I'll leave that for the chat. You can tell me what is the answer, or what should I do? Either one's good, without looking at the assignment, because the assignment already has the answer posted. But what is the answer, or what should I do? How do I find that f of x? X to the 8th. Take its derivative. These sound like good answers. Let's try. Okay, so that's the idea. If I'm reading that right, the integral is 1/9 x. We just integrate it to find f of x. Yes. So again, we want to go from, we've integrated, and we want to find out what that is. So to do that, so again, we've done here is we've integrated. And to go backwards, we differentiate. So taking that derivative, I'll even include the c, which is the constant. If I differentiate that, this drops down by a degree, so I get not 9 anymore, but 8. And the 9 comes down in front. Does it come down in front? I can also tell you that the constant is 0. Yep. So the 9 comes down, we drop the degree, so then I'm left with 8. So x to the 8th. So that's what I expect. Yes. So therefore, I'd expect it to be x equals, f at x equals 8x. Okay. Because what had thrown me, and I should maybe, I'll white this out, because I had copied it incorrectly from the assignment. So what the actual question had written. So this is good. Just to make sure that there's no discrepancy between what we've done in our tutorial and what's on the assignment. What the I had just copied it down incorrectly, so I have it as 1/3 x to the 9th plus c. So same thing again, you can just differentiate that to check. Nine divided by 3 is 3x, and that should be a 0. And that's what we have for number 5. Okay. For number 10, oh sorry, this is page 10. So this would be like this is exercise 6. So we're asked to check the formula x times x plus 1 to the 6th dx is equal to 1/56 times 7x minus 1 times 1 plus x to the 7th plus c. So again, to check this, to make sure that we get to this one over here, we'll have to differentiate that. Okay. So what I'll do first is I'll write the 156 out here. And now I have to differentiate this. I won't worry about the c because that's 0. And now I'm going to have to apply the product rule to this. And if I have two functions, f and g, it's the derivative of the first function times the second plus the first function times the derivative of the second function. Okay? So that means the derivative of the first function, so that's just 7. Is everyone okay with that? 7x minus 1, so the derivative of that is just 7 times the second function unchanged plus the first function times the derivative of the second function. So in this case I have 1 plus x to the 7th, so the 7 comes down. I'm using my chain rule. The 7 drops down by a degree, so it becomes 6. And the derivative of the inside is 1. So let me just clean this up. I think I'll leave that 7. Sorry, maybe I didn't have to do so much here. So I see that I have a 7 and a 7, so I'll bring that out in front. So I have 7 over 56 Oops, I gotta make sure I... Okay. And what I would do is I would factor that out so that I got 1 plus x to the 6. And so what I'm left with is 1 plus x plus 7x minus 1. I know I'm writing a lot of steps. So I have 1 and a minus 1, so that cancels. And then I'm left with x plus 7x, so that's 8x. And, oh, yeah, we're almost done. 7 times 8 is 56. So I'm just left with x times 1 plus x to the 6. So that's just 1. Okay, I'll make sure I'll say that's 1. So that I'm left with x times 1 plus x to the 6th. And so yes, what we have done is we've actually shown that this is true. So again, stuff like this, just I would say, if you've done enough practice, just relax. Like just take a breath, and while I never have done this like this question myself, I took the time and just made sure that I was following all of my rules, and just I know, while it may look like I took a lot of steps, if you start to rush things or if you start to drop a negative, your proof, that's what we've essentially done. We have done a proof here. Starts to fall apart. And you know what the end result should be. And after you've done all your manipulation, you get the wrong result. Well, your proof is incorrect then. So what we've done here is we've applied the product rule, and in here, that was the chain rule. Then from here to here, we factored out a 7. From here to here, I factored out a 1 plus x to the 6, so that's right here. So we saw here, we have here and here, so that came here. We simplified. From here to here, 7 times 8 is 56. And we got our final result. Is there any questions about what I did there? Maybe I'll push that up so if people were writing. Oh, could you read the bottom line in plain English, please? This one right here? Or which line? Okay. So I would say, therefore, the integral of x times 1 plus x to the 6, well, the integral of x times 1 plus x all to the 6 dx is equal to 1/56 times 7x minus 1 times 1 plus x all to the 7th plus c. So that's the integral of x and dx. You can also say that that is the integral of x 1 plus x to the 6 with respect to x. So again, this is the operation that we were telling me. So we're going to integrate. This is the function that we're going to do. And I'm telling you that we're going to take this with respect to x. The reason why we always, okay. The reason why we usually write, you know, what we're taking the derivative or the integral with respect to is because sometimes you might not have a function with just one variable in it. So, for instance, if I have this integral, I'll go x squared plus 2x plus y. And I'm telling you to take this with respect to x. What this says is, okay, I'm going to apply my integral rules like I usually do. I can do the 1/3 x cubed plus x squared. So I got 2 over 2. So over in this line here. And now I'm asking you to take the derivative of y with respect to x. And at that point, you treat this like a constant. You treat y just like a number, like pi, like 4, any number. And so you treat that like a constant. because we're not integrating with respect to y, we're integrating with respect to x. Y is not changing. It's the x's that are changing. So you treat it like a constant, so it's just like y times x. Plus a constant, our integration constant. You know, if I do the same thing, did I miss it or did we just not do? No, we did not do partial differentiation this year. Nope. We didn't do partial derivatives this year, no. This year was shorter. So, but what I can do is show you why we keep using functions like this. If I have a y of 3t squared, if I take the derivative with respect to t, well, what we're going to do is we're going to do that right now. Right now I have y equals 3t squared, and that's okay. We can take that derivative. That's okay. 3 times 2 is 6, becomes t. But if you did something weird, like you did dy by dx, or for instance, you put that in the computer, you put it in like y equals 3t squared, and you asked what the derivative is with respect to x. There's no variable x in here. So, because there's no variable x to differentiate with, that derivative is equal to 0. So, you can have 4t squared plus, let's say something else like 9x, and we'll just make this to the 3. If you want to do the derivative, we can do the derivative with respect to t. So doing that, the only term in here that is of interest is this t right here. So 4 times 2 is 8t, and that's it. But I can also take this y function here with respect to x, and I don't look at this because this is t, it's a constant, the derivative of a constant is 0, and I'm only looking at this term right here. So I have 9x cubed, so that's 27x squared. So again, this tells us what variable to integrate with respect to. I know it looks kind of funny when there's only one variable and you're told to integrate. Why are we writing this dx? It is a little bit of a formality, but it does tell us what variable to integrate with, because you may get a function that does not necessarily have only one variable. It could have 2 variables. So again, that's what that dx is telling us. in this case, we have this y. It's telling us to differentiate with respect to t. If we add some other variable x, again, that's 0 because there's nothing in there. But again, if this function here, we have y, you know, that is a function of two variables, then I can take it with respect to t, or I can take it with respect to x. Okay. Basically, that's what I've done here. So, quick intro to partials. So the idea is that you have a function that is in 3 dimensions now. So you'll have okay. So over here I say I would have x and I have a y. So I have a Cartesian coordinate system here. And over here I would have z. And you can have something like you have something like that. So what you end up having is a two-dimensional function. So you can have, say, z is equal to f. Here's a function of two variables. And you could say have like x squared plus y squared. Then if you wanted to take the partial derivative, they switch to a different symbol. They'll use a curly d like this. So that means partial. And so I'm telling you, I'm going to take the partial derivative of f, and I'm taking it with respect to x. So same idea. I look at this function here, which is a function of two variables, and I will differentiate this with respect to x. So here I have x squared, so that's just 2x. And I have y squared, but there's no x, so I don't care. It's a constant in my opinion. Or not in my opinion, it's in how I'm interpreting this with respect to x. Then the other partial that I can take is with respect to y. And I treat the y as my variable and my x as a constant. So again, x squared, that's a constant, so I don't have to worry about that. And I'm looking at this variable now with y, and that's just now 2y. You can take it again, so we have the second derivative of this function with respect to x, that's equal to 2. And same thing over here. So again, you can take derivatives in more than one dimension. Oh, okay. So then he asked, okay. Then the question that we had. So what I'm going to call this is I'm going to call my function f of x and y x times y squared. So that's what the audience wants, and we will differentiate that. So taking the derivative of that with respect to x. Again, I treat the y squared as a constant. So again, okay, I'm quite happy. The course does not need, okay. Yeah, so you can just take the derivative of that. And so the derivative of x is just 1, so that would just leave me with y squared. And taking the derivative of that with respect to y becomes 2yx. Okay, well, that was fun. The reasons for why you'll end up using higher dimensional derivatives is when you start to get into optimization in your business courses. They require you to use first order conditions, second order okay, without getting into that. But yes, you can take what we have learned in this calculus course for one dimension, and you can scale it up to higher dimensions. So, but it just means that when you're taking the derivative with respect to one variable, you're just treating the other variables like a constant. So we've done quite a few of exercises. Again, check out on the Moodle page, we have lots of other exercises from the from the textbook, as well as questions I've added as well with the answers beside it. And if you get stuck, again, feel free to send me an email. I can write out this solution for you, or correct or check out what you've done. And I think that should be the end of our tutorial. Thanks everyone for tuning in for our 4th tutorial. And we have our last lecture/review on Thursday. Take care everyone, and have a good night.